All right, so far we've looked at individual neurons and models of how individual neurons behave. But, of course, the magic of a neural network is how they interact with each other. So the goal today, in this lecture about synapses, is to get an overview of how neurons pass information between them and how we can model those communication channels. So, when a neuron fires an action potential, the wave of the action potential or the wave of electrical activity travels along its axon. So, quick review here of the anatomy of a neuron. We have dendrites over here. We have the soma, like the body, in here. And we have the axon here. Now, over here, where the axon sort of interacts with dendrites of the next neuron, these are synapses. The junction where one neuron communicates with the next neuron is called a synapse. So let me give you the story of what happens when an electrical impulse, an action potential, arrives at a synapse and how the information travels from the presynaptic neuron through the synapse into the postsynaptic neuron. Okay, so first of all, on the left here is the presynaptic neuron. So step one is we have a presynaptic action potential. A presynaptic action potential. All right, so that causes the release of neurotransmitter. So in this synaptic terminal, we've got a bunch of vesicles. Vesicles or vacuole? Vacuoles, I think is the right word. Vesicle, I think, is a little tube. What they do is these are like little bags of neurotransmitters, special chemicals, and they merge with the membrane of the cell itself, and they release, I'm just showing a bunch of different stages here. They release the neurotransmitter into the synaptic cleft, the space in between the two neurons. So a presynaptic action potential, I'm going to have to write a bit smaller here, causes release of neurotransmitter. Release of neurotransmitter, which then gets into the synaptic cleft and binds to receptors on the postsynaptic neuron. So I'll draw them like this, like little receptor things on the far side of the postsynaptic neuron, so they can bind in there. So that goes to here, and this, let me move this out of the way a little bit. And that leads up here to, so presynaptic action potential causes the release of neurotransmitter, which binds to receptors on the postsynaptic neuron. Now that binding operation kind of changes the molecule of the receptor. All sorts of different things can happen. But basically, it changes the electrical activity of the membrane in the postsynaptic neuron. So step 4 is that this binding, let's see, which binds to receptors on the postsynaptic neuron, opening ion channels, and changing the membrane potential. Of the postsynaptic neuron. So that gives you the quick story. Action potential arrives, releases neurotransmitter, which binds on the postsynaptic neuron, causing a change in behavior. Different ion channels open and close, basically, on the postsynaptic neuron. And we've already seen in the Hodgkin-Huxley model how ion channels opening and closing can change the membrane potential of a neuron. Okay, so even though an action potential is very fast, the synaptic processes by which it affects the next neuron takes time. So some synapses are fast. They take about 10 milliseconds for the entire process of ion channels opening and closing to happen. Some are quite slow. Sometimes there's this whole chemical cascade where one chemical binds to a receptor, which releases another chemical, which binds to another receptor, which binds to something else, which then opens or closes some ion channel. So these are called like second messenger receptors. So these things can take 300 milliseconds, still really fast, but in the molecular scale of things, it's pretty slow. So we wrap this all up into a single number. We represent that time it takes for the signal to sort of get into the postsynaptic neuron as tau sub s. So then the current entering the postsynaptic neuron can be written as a function h of t. So it's a function of time. And we'll write it k times t to the n e to the negative t over tau s. If t is greater than or equal to 0, now this is for some n, a positive integer. Tau can also be 0 actually. So let me do this. Greater than or equal to 0. And it's 0 otherwise. So what this means is that the reason we have a split between t less than 0 and t greater than or equal to 0 is because the once the signal arrives, at least in terms of this filter, this h function, the spike arrives at the synapse at time t equals 0, and then what we're looking at is what happens after that. So k is chosen in order to make the integral under that function h of t equal 1. This is just more of a sort of mathematical convenience. So the integral from 0 to infinity of h of t dt equals 1. And so according to the formula I have above, you can work it out if you like. I've written my k a bit differently, it doesn't really matter. Equals 1 over n factorial tau sub s to the n plus 1. I think I mapled that. Okay, now what does this look like? I'll give you the general look of what they look like, especially for n equals 1 or 2. It's got this parameter here, this n. So for n equals 1 or 2, this is a smooth function that tends to look sort of like this. First, I'll draw a really short time constant. So this is tau s about 10 milliseconds. So really quite quick. Maybe I should have even drawn it thinner than that, but you get the idea. Maybe I will draw it thinner than that. Something like that. As opposed to, so this could be a neurotransmitter like AMPA or GABA. If you don't care about the actual chemical names, then that doesn't matter. Then there are slow neurotransmitters that can take hundreds of milliseconds. So those look like this. So this tau s is equal to more like 50 or 150 milliseconds. And NMDA is an example, neurotransmitter that does that. The area under both of those curves is supposed to be 1. Okay, this function h that I've just drawn is called the postsynaptic current filter. Or, in keeping with the ambiguity between voltage and current, because we're dealing with sort of fixed patches of membrane, the distinction between voltage and current, for a fixed patch, you can go from voltage to current and back and forth. So I don't know much about electricity. Maybe you do, maybe you don't. I'm not going to dwell on it. Current and voltage are kind of the same thing in the context of what we're talking about. So H is the postsynaptic current filter, or we often call it the postsynaptic potential filter, where potential means voltage. Okay, I'll usually say postsynaptic current filter. Okay, so multiple spikes form what we call a spike train, and they can be modeled as a sum of Dirac delta functions. So each spike is represented by a Dirac delta function. I'll define that in a second. So if we have time here, and we get spikes coming in here. There's a spike at t1, maybe a spike at t2, a spike at t3, and so on. And we can represent the activity of a neuron as the sum of its output spikes. So p equals 1 to 3 in this case, d delta of t minus tp. So the TPs are down here. Those are times of the spikes. So that function on the left there is a of t. It's 0 everywhere except Dirac delta spikes at particular times. So in case you're not sure what a Dirac delta function is, it's equal to 0 everywhere. I'll say 0 otherwise, but it's equal to infinity when, let me put it this way, if t equals 0. So it's equal to infinity at 0, and it's 0 otherwise. But there are many different types of infinity, many different sizes of infinity. This is chosen so that the integral under this spike equals 1. And it has this nice property that if you integrate some function times a Dirac delta function, that the only thing that comes out of this integral is the value of this f where that delta function, where that spike happened to be. So in this case, that spike is offset to be centered on capital T. So in this case, it just reads off f of capital T. Okay, so we use those properties of the Dirac delta function in a minute. So how does a spike train influence the postsynaptic neuron? We got the spike train in the presynaptic neuron. What's happening in the postsynaptic neuron? All you do is you add together all the postsynaptic current filters, one for each spike. And this is actually the same thing as convolving the spike train, that A function, with the postsynaptic current filter. So here's a little pictorial example. I've got this function A of t here, and it's a spike train, a bunch of Dirac delta functions. Now I'm convolving. This star thing here represents convolution. I won't go, well, you'll see what convolution looks like in a second. You probably already know. So we're convolving that spike train with the PSC filter, H of t, the postsynaptic current filter. When you do that, it basically creates a copy of that filter on top of every spike. So I've shown here in this light gray sort of my thought process, where I put a copy of one of those H functions on where every spike is. Now if I add them all together, I get, this first spike is here by itself, but once I get to the second spike, now I have to add those two H functions together. So I'm going to be a bit above the second spike. That was probably a bit too much. Let me redraw that. Now I've got another spike happening, so I'm going to add together those two. That maybe is too much again. But you get the idea. You add them together. So this would be S of t. This would be the filtered spike train. Okay, you have convolution of the spike train with the PSC filter. So S of t, this postsynaptic current function, can be written as A, the spike train, times H, convolved with H, and the result will be a function of time. So sum over spikes of H at t minus Tp, which equals the sum of the postsynaptic current filters. One for each spike. Here I'm showing just an image of graphic of a bunch of spikes shown with a raster plot, all those little red lines there. It's a raster plot showing when the spikes occur because it's a time axis along the bottom there. In blue, I'm showing the postsynaptic current that's induced by this spike train. Now, of course, I have to assume a particular synaptic time constant, and also chose that n value. I believe I'm choosing an n value equal to 1 here. I'll show you an example in a second. So that's just an example. You can see how multiple spikes together cause a large increase in the postsynaptic current. So let me show you a demonstration. Here's a script that I've written. So it has lots of code in it, and I'm going to be calling code in this other little module that I have. Don't worry about it. Just includes a lot of stuff. A lot of the stuff is here though. Synaptic filter, this basically just implements that, that H function that I drew for you, or that I wrote the formula for. So it takes a tau sub s, synaptic time constant, and it takes an n. And you can see there are some default values there. Error. I didn't run that one. So here it's showing for a particular time constant what the postsynaptic current filter looks like. If I increase the time constant, you can see it gets wider but lower. So you can see what that looks like. So when there's one spike, here I some code just for demonstration purposes. When I have one spike shown by the location of the spike shown by the green, you can see the postsynaptic filter kind of drags that activity out. So the spike arrives, boom, but the postsynaptic current takes some time to roll out over time. So what about many spikes together? So here are a whole bunch, and you can see how the blue line, the postsynaptic current, sort of goes up and down as the firing rate, as the number of spikes that arrived recently changes. So here's a slightly, I think, a better example showing a widget where I can change the postsynaptic current. So remember, there's one of those postsynaptic current filters that starts at the arrival of every spike. Now, if the postsynaptic if the synaptic time constant tau sub s is small, that means that there's a very short-lived, very spiky postsynaptic filter that starts on each spike and then but dies off really quickly. So this really just becomes like telling the postsynaptic neuron, spike occurred, spike happened, spike, 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 as opposed to a longer time constant, a longer synaptic time constant, which is now no longer reacting to individual spikes so much as it's sort of adding up the recent history of how many spikes occurred. So along here in the middle here, that's kind of, the spikes are few and far between. So the postsynaptic current is kind of at a low level. You can actually sort of see what the postsynaptic filter looks like. But when the spikes start arriving quickly, you can see the postsynaptic current filters start to pile up on each other, and you get this sort of higher sustained postsynaptic current induced by a volley of spikes arriving in quick succession. Finally, if we have a constant firing rate, you can see that they will add up together. Now I've just chosen 50 milliseconds, but the story is pretty much the same if I choose a longer time constant. Just for your own satisfaction, let me choose 200 milliseconds. It's climbing up to the same value, it just takes longer. 20 milliseconds. What we're seeing is that this the constant barrage of presynaptic spikes is causing the postsynaptic current to sort of climb to some steady state value and stay there. Now the steady state value it's coming to, it looks like it's about 60. The postsynaptic current is 60 units, whatever those units are. It's yes. I set the spike rate of the presynaptic spikes to be 60 hertz. What happens if I change them to 30? That's not the right plot. Whoops. Where do we go? Oh, yeah. My function is set up so that if I give a presynaptic firing rate less than 60, it randomizes the timing. What if I give it 80? So, okay. You can see the postsynaptic current rises to 80 units. So the postsynaptic current, because each postsynaptic current filter carries 1 unit of current, then the postsynaptic current will converge to the number of spikes per second that it's receiving. And so the purpose of this demonstration is to hopefully convince you that there is a link between spikes and a real valued firing rates. So I haven't really talked about this yet, but we will come to a point very shortly where neurons are basically considered to be numbers. So a neuron, you can talk about the activity of a neuron being 0.7 or 0.23 or 0.02, some real number, often in the range between 0 and 1, but it doesn't have to be. So how do we reconcile the fact that neurons actually send spikes and these numbers that we're using to represent the activities of neurons? The key is that when neurons are spiking regularly, the postsynaptic currents that they induce in other neurons climbs up to some steady state value, or is basically some sustained value. So the postsynaptic current that a neuron has is often a representation of the presynaptic firing rate. Not necessarily spike, 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 spike the timings, but the rate at which the presynaptic neuron is firing. Now, if the synaptic time constant is really short, the postsynaptic current will be really quick, just representing a bunch of individual spikes, as this demonstration shows here. Oh, I can't do that now. So the postsynaptic time constant is really short. If the synaptic time constant is short, the postsynaptic neuron will just see a bunch of quick injections of current as if spikes are arriving. If the synaptic time constant is long, the postsynaptic neuron instead will receive an input current that reflects the recent firing rate of the spike trains leading into it. Okay, let's talk about connection weights. So the question of a connection weight is how much does a spike at the presynaptic neuron influence the input current for the postsynaptic neuron? The total current induced by an action potential onto a particular postsynaptic neuron can vary widely, and it depends on things like the number and size of synapses. There might be multiple synapses from one neuron onto another. The amount and the type of neurotransmitter that the presynaptic neuron releases, or the number and type of receptors on the postsynaptic neuron. All these factors change how much a presynaptic spike influence a postsynaptic neuron. So we, as mathematicians and computer scientists, we take all those and ball them up into a single concept of the connection weight. So we combine all those factors into a single number, the connection weight. So thus the total input to a neuron is a weighted sum of filtered spike trains. So here I've got neuron A and neuron B both synapsing onto a neuron C. And you can see this little connection thing here. That's a common way for people to write synaptic connections. I won't use it that often in this course, but at this point we will use a little bit. So the weight, W, to C from A. This is the weight to C from B. Each of those two different connections have different weights. So when we have many neurons, it's actually helpful and convenient to sort of have a way of writing down all those weights. So suppose we have two populations, X and Y, and X has N neurons. Here I'm drawing it as 2 on the left. Population X. And population Y, which I'm showing here as 3 neurons, but we can say more generally has M neurons. If every neuron in population X projects to or synapses onto every neuron in population Y, then we will have N times M total connections. Each with its own weight. So here I've shown them all like in this little diagram. And so it becomes really helpful to write them in a matrix form. So this matrix here will have W11, W21, no, W12, W21, W22, W31, W32. And we'll call this matrix W, and it's an element of Rm by N. So if we store the neuron activities in vectors, so if X vector is X1, X2, and Y vector is Y1, Y2, Y3, then we can compute the input to the nodes or the neurons in the second population, the Y population, using matrix vector formulas. So the input current Z is W times X plus a bias, where B holds the biases for the nodes in population Y. So a bias is sort of a catch-all for influences on the neuron that are not accounted for by the connections that we're modeling. So this neuron here, for example, Y2, has input from X1 and X2, but it also has other chemical processes going on. I mean, a real neuron would, as well as there might be other inputs to that neuron that we're not actually drawing. Maybe there's some other population that's inputting. So as a catch-all for all these different things, and it's actually like a sort of computational mathematical fudge factor, I guess you could say, we put all those into this sort of bias term called B. So the input current, Z, for those nodes or neurons in population Y can be computed W matrix times the vector X plus vector B. So thus, Y, the activity of the nodes in that population Y, is equal to sigma of Z, where sigma is the activation function. Could be arctan, could be hyperbolic tan, it could be logistic function, it could be the tuning curve for the LIF neurons. So sigma of Wx plus B. Okay, so that's how we go from one layer X to the layer B. To layer Y. Now, another way of representing this, it's kind of annoying that we have this B thing here, this sort of vector off by itself. So as you'll see as we go through the course, we have to treat W and B separately in terms of how we tune our networks. We have to tune W and we have to tune B. They're different entities. Turns out we can actually put them in the same sort of mathematical context, and here's how. Imagine that we had another sort of magical neuron here that was always equal to 1. Its activity was always 1. And we connected those to our population Y as well. And we gave them connection weights B1, B2, and B3. So then, come on, stop moving. So W times X plus B can actually be written as this, I'll define this matrix blockwise. So the last, I'm just sort of adding on one more column with those B values in it. If I multiply that by this vector, which has X in the top part and then an extra little 1 at the bottom, I just added a 1 as another element in that vector, it achieves the same action as the W X plus B. So it's an augmented matrix. So sometimes I'll use this format, sometimes I'll use this other more explicit format. They're the same thing. Okay, so implementing connections between spiking neurons. So now we know how to represent the matrix vector, sort of how to encode a whole collection of connections between two different populations. Let's just finish off how the model of a neuron, now that we know more about the input current. So for simplicity, for this particular derivation, I'm going to let n equals 0. Remember, we had these different postsynaptic filters. Now this was for n equals 1 or n equals 2 or something. They all look kind of the same. For n equals 0, it's kind of a special case. We get this, let me just draw it separately. At the spike time, we get a sudden jump up to a value of 1 over tau s, and then it decays according to tau s. So this is the time axis here. So it's a jump discontinuity, but the decay happens smoothly. So this, if you look at the formula I wrote before, setting n equal to 0 gives us this formula. So this is simple exponential decay. The only thing that's not realistic about it is this sort of jump that happens, this discontinuity. But it makes our lives easier when it comes to actually modeling these. So that function, h of t, happens to be the solution to this following initial value problem. Tau s times ds by dt equals negative s, where s of 0 equals 1 over tau s. Proof? You know what to do. You should know how to prove that that is a solution to the initial value problem, that this h of t is a solution to the initial value problem there. Okay, so the full leaky integrate and fire model looks like this. We have all these incoming weights, wij, and they're contributing to this postsynaptic current, which I'm calling S. So we're looking at neuron I, basically. So the index I is because we're looking at neuron I. So S of t is basically adding up or integrating all these input spikes, or integrating the input spikes and turning them into a postsynaptic current. So S is a postsynaptic current. Now that postsynaptic current is going to cause the neuron to spike, which will make V, which will set the value of V. The postsynaptic current is going to change the membrane potential, which is what V is. And then that V, when that V reaches a threshold, it will spike and send a spike out the axon. Okay, so the differential equation we had for V before, now that we know what our input current is, S sub I minus V sub I. Now this is if the neuron is not refracting. That means if it's not in its refractory period, then it's going to be integrating its input current. And now the input current, its dynamics is that it decays over time. And we'll address the arrival of spikes in a second, but if no spikes are arriving, it's decaying over time. So first let's look at the activity of the neuron. If V sub I reaches 1, the threshold, we do a few different things. We start refractory period. We also send a spike along the along the axon. Along the axon. And finally, we reset the membrane potential to 0. So what happens if a spike arrives? So this is if the neuron I reaches its threshold, it sends a spike out. What happens if a spike arrives? We have to update our input current accordingly, right? So if a spike arrives from neuron J, we increment S sub I. So S sub I gets the old S sub I plus the weight divided by the synaptic time constant. So the amount of current that it injects into the postsynaptic neuron is proportional to the weight, and we divide by tau sub S. That's that normalizing factor, so that the total amount of current that eventually gets injected is 1. Well, 1 times the weight. So I have a demonstration of this scenario. Remember, we have neuron A and neuron B synapsing onto neuron C. Neuron A and B synapsing onto C. Okay. So I've got a couple different spike trains. One's spiking at 9 hertz and one at 12 hertz. I believe that's what that means. This number of spikes. Okay, anyway. Here I've got the weights. The weight going to C from A is 0.4. The weight going to C from B is negative 0.25. So you can actually have a negative weight. How? Some neurotransmitters actually block the postsynaptic neuron from accumulating membrane potential. Essentially sort of opening up some channels to let some of the current out, I guess. I'll just keep it at that. But so you can have postsynaptic currents that are either positive or negative, just depending on the receptors and the neurotransmitters and all that stuff. Okay, so I'm going to create the spike. I'm going to create the postsynaptic currents for each of those 2 spikes. I'm using the same time constant. And what I'm showing here is the spikes, the spike raster for neuron A, as well as the postsynaptic current induced by neuron A. And I'm showing the spike raster for neuron B and the current induced by neuron B, the postsynaptic current induced by neuron B. So from neuron A, it's positive. From neuron B, it's negative. If I add those together, I get this black curve. See, before neuron B fires, it's the neuron C is just receiving stuff from neuron A. But once B starts firing, it's now a competition. It's kind of a push and pull, tug of war between the positive influence of spikes from neuron A and the negative influence of spikes from neuron B. Here I can adjust the weights. If I turn down the connection weight from neuron A to neuron C, you can see the influence of A goes down. In fact, I can make A an inhibitory neuron. So now A and B are both inhibiting neuron C. So we get lots of negative current. Or I can also play with neuron B. I can make it an excitatory neuron so that it combines with A to excite the postsynaptic neuron C. So I hope that gives you a feel for how multiple neurons can synapse onto another neuron and how their spike trains combine by adding together the postsynaptic currents that are induced, the weighted postsynaptic currents induced by each of the incoming neurons, each of the presynaptic neurons. It's a mouthful.